last speaker is Ravi Prakash. He is assistant professor in the University of Concepcion in Chile, and also as a visiting professor position in the Universidad Federal de Paraíba in Brazil. He got his PhD in 2013 with in Bangalore under the guidance of Professor Nanda Kumaran. He is mainly interested in homogenization of optimal control problem and optimal design problem. And recently also is exploring the area of inverse problems. He has more than 20 publications, 20 talks in international meetings, and 2 PhD students already discussed, obtained their thesis. Okay, so please, Ravi, you can go on.
Okay, thank you very much, Patricia, for the long introduction. Thank you very much to organizers for the opportunity to give a talk. I wanted to explain many things which appeared in this conference, and there are lots of unasked questions which I wanted to explain. So thank you very much for the opportunity. And of course, in the pandemic, it is very nice to see you all. Even I came to know many people who are very closely working to the area which I am interested in. So, and the benefit of the corona is that we have every talk online. So even if I'm sleeping, when I get up, I see the talks. Okay, so let's start with the talk. So the topic is unfolding operator in locally periodic domains. Okay, so this part of this talk is locally periodic. I will come later. Okay, so first of all, stick with the periodic part, periodic oscillating boundary domain. And in the periodic oscillating boundary domain, the motivations comes from many. Few is just one is here, just heat radiators. So if you see here, there are notches. Okay, the periodic notches, and in comparison to the dimension of the domain, they are very thin but with the fixed height. Okay, the circular version of the same but with the branched. So in the circular version of this heat radiators, if you see, every notch has 3 sub notches. Okay, so this, in this sense, it is a little bit different than the COM type structure. So if we draw it in the 2-dimensional figure, here we have 4 types of domains, which I want to explain before going to the locally periodic domain. Yeah, so first domain is I will explain where I saw it. There are lots of it means people studied such domains. So when I saw first time, it was the paper of Mayo, this domain, Umberto. Yeah, and this domain is the paper where I saw first time was the paper of Taras. And then I keep continuing in this direction and this direction. So let's understand these 4 domains first. So in the first domain here, if you see, the height is fixed. Okay, and there is each notch is of epsilon order in the dimension of x1. Right, so epsilon. So we have a reference teeth, and then we scale it by epsilon in x1 direction and then place it periodically. Correct. So the height is fixed, but the periodicity of epsilon order comes into the x1 direction. Okay, and the below I have a omega minus. If you can see a omega minus, and this omega minus is the fixed part on the domain. Okay, and epsilon here is a very small parameter which will go to 0. So basically asymptotic analysis when epsilon goes to 0. So in the what is the property of the second domain here? Here, if you see, this is the similar structure like the first domain, but in the each epsilon period, we have branches, right? And because of these branches, the limit problem has different characters, okay? And definitely it captures the limit problem will capture the character of the domain. Okay, in the third domain, if you see what is the difference in third domain with respect to other two domains? That if you see that there is the teeth has do not have any corner. It is not touching. But here I am allowing it to touch. Okay, at the same time, is circular version here also I am allowing it to touch. And we have branches as well. So these all characters affect the limiting analysis, and finally the limit problem is different in each case. Okay, so this is the mathematical issue which we deal generally when we study asymptotic analysis, asymptotic of the PDE, asymptotic behavior of the PDE in such domains. Okay, so the story starts like this, something like 10 years before when I started doing my PhD. So even if I remember correctly, Patricia suggested to study the optimal control problem. We never studied that problem because she was suggested in the loose connection material, right? If I remember correctly, and then but we studied the optimal control asymptotic behavior of the optimal control problem in the first domain. Okay, and we applied the control away from the oscillating part. It was quite practical, but we could not get the characters. We could not get the characters at that time. Many ideas came from anyone, something like hand waving ideas, like consider the optimal system like one system and then try to find the character estimates. But it's all was just in the air because many I investigated a lot, and I understood that for the character estimates, even results were not available for the classical cases like composite materials. So we stopped at that moment, and the problem is still open. The optimal control problem with the characters for the optimality system in the when the control is away from the boundary. Okay, then we switched to other types of controls. Okay, so when we switched the other controls, I finished my PhD and Vidhan started his PhD. So we tried to put the control in the oscillating part. Okay, and the idea was to study the different type of optimal different type of controls, periodic controls, locally periodic controls, and try to get the optimal control. So try to get the optimal control and then compare two different optimal controls and get the optimal of the optimal controls. Yeah, so that problem is still on. We are still thinking about it. But the idea was, but from there, since the domain was periodic, we were interested in putting the periodic controls, correct? And then what happened, we realized that if we use unfolding, we can characterize the optimal control. Okay, and the boom. And then we started to characterize the optimal control using unfolding. So the very, very general results got by Taras, which he was mentioning last in the talk of the Rajesh. He got very, very general results, but we were trying to get weaker results, but using unfolding. Why? Because we were interested in the characterization of the optimal control, the periodic optimal control. Okay, so in the talk of the Rajesh, he just eliminated, he used the homogeneous data, right? If you remember, he was pointing out the homogeneous data, but actually there was a periodic data. Okay, and why that was a periodic data? Because we were finally aiming, which got published later, to consider the periodic control. Okay, and that's why we were even getting the weaker result, but we were trying to use the unfolding and then get the then apply that idea for the control, periodic control. Okay, that story was fine, and Vidhan finished his PhD. That story got over, and then when in the parallel terms I was learning shape optimization and topology optimizations, right? So in that case, I wanted the oscillation in the top part to be smooth. Okay, and here the story comes when I wanted to generalize for the corner type of, no, it means who allows to touch the graph. The profile is like having some corners. Okay, so but quite a long time we could not do it. And recently we even that result is not appearing. There are lots of issues which I will talk about later, that if you have the corners, you have to deal with it. Okay, and then Bidhan Ayyappan started his PhD. So he actually, in his first paper in 2017, I guess, he proved that the unfolding operator can be adopted for the branch structure, right? So even in the papers, I was demonstrating the branch structure, but analysis was done for the single notch. Okay, it was not having branch. So why it is that? Because from the paper of Vidhan, from the paper of Ayyappan and Nandakumaran, it was clear that if I can do it for the one notch, the unfolding can be adopted for the several branch, and we can do the analysis. So to keep the presentation simple, we presented the photo like with multiple notch, but the result was only for the one notch, a single notch. Okay, so and that also was true for the circular domain. So if you can see the circular version of the domain, it is here in the fourth one. Okay, so like this the story goes. And then what I was mentioning, that I wanted to study the shape optimization problem, right? So so I wanted the oscillating part to be really really general. It can have corners, it can have notches, many, blah blah blah. So for that, because I wanted, why I wanted that? Because in the shape optimization, I wanted to calculate the shape derivative. Okay, that project is still on, and I need we work here. We started working here or with the multi-scale FEM to actually calculate and see. But I am not an expert of FEM. I just recently get involved with optimization. So this really long project is going on. But I prefer to answer all these questions because the history, because the idea was starting from 10 years and it's going on. Okay, so so the details we can see here. So the unfolding operator. So unfolding has very well explained by Carmen, and then before also Rajesh explained it very well, the unfolding. But I'm giving the reference of the paper by Damlani and Peterson, which was the periodic unfolding for the oscillating boundary domain. Okay, and the idea was pretty much similar. Okay, so this unfolding, so all the history of the periodic case led me to study the domain with the very general oscillating profile. Okay, the profile of the oscillation of the oscillating boundary domain should be I was interested in very much general. Okay, so there I started thinking about locally periodic oscillating boundary domain. Okay, so when I started thinking, I got this paper by Maria Patasnik. Okay, and this was some sort of like middle of the PhD of Ayyappan. Okay, and he did a fabulous job in the analysis of this. So in this domain, if you see here, it was like some sort of man-made oscillating locally periodic domain. Why I'm saying that man-made? Because here, if you see, there is a epsilon period, okay, and in each epsilon period there is a mesocell. Okay, for example, two adjacent epsilon has a different type of periodic scaling. So in each microscale there is a in each microscale there is a micro scale. We call it in the article, we call it as a mesoscale. Okay, so in each period, for example, if you see here, there are three notches, right? And in each notch you have sub notches. But this thing, as I told you, that from the paper of Ayyappan and Nandakumar, it was clear that we can adopt the idea of branches, even if we analyze, keep the analysis simple and do it for the one notch. So this domain was little bit different in the sense that it was some sort of start of our thinking towards the direction of locally periodicity. So each period epsilon period has some mesocell type of periodicity. Okay, and the lower part, of course, omega minus is fixed. There is no issue in omega minus. And then we try to understand first that what is the asymptotic behavior of this. Again, here, if you see, the notch is touching, but in the paper, the notch was separate. Okay, the corner were not allowed. But at that time also, we were knowing that if the notch touches, there are some issues, and we were not able to fix it. Recently, something, even yesterday, I was talking to Ayyappan. He was telling me that whatever we took for the granted, we can prove it, and in the paper, in the coming papers, it will appear. Okay, so I hope the domain is clear, right? It is some sort of man-made in the sense that I constructed, motivated from this paper, such domain. Okay, this is not so naturally locally periodic. We will see if later that what is the very much general form of locally periodicity. Okay, so here. So first we wanted to do the locally unfolding, because we had success in the periodic and with the unfolding. So we started thinking how to apply the unfolding for such domain. So if you see here, it is the same idea, but in the definition of unfolding, this part is actually the so I am dividing the unfolding in each epsilon period, and each epsilon period I am defining it using the mesocell. Okay, so here if you see, limit domain is omega u. Omega u, as was indicated by Rajesh, that unfolding allows you to get rid of the selection of the test functions, but at the same time it adds the dimension. Okay, so here if you see, the problem was in 2 dimension, 3 dimension, and then it became the 5 dimension. Okay, so it added here the 2 dimension more. Why it added 2 dimension more? Because it has the to capture the locally periodicity behavior. Okay, so few notations we should keep in mind. What is omega u? Omega u will be the limit domain, and the limit domain has a reference R2 reference cell, and then G is the profile which counters the profile of the oscillation. Okay, and the profile is defined by eta. Okay, and here d epsilon h epsilon k is the mesocell, which is different in each epsilon cell. Okay, and so like this we just generalize the definition of the unfolding, and then once the unfolding was generalized, we tried to verify the properties of that, because we wanted to use it for the analysis of a Laplacian problem actually. Yeah, so these things were very easy to prove, the first few, second one was not difficult. What happened here in the change of derivative also, there was not a problem with respect to x3, but when we saw the derivative with respect to other variables, right, it was something different and then earlier properties. Why? Because and it has some meso scale was contributing in the change of derivative. Okay, so here at this point it became it looked like it became interesting. Okay, so properties we continue to verify for u in L2 omega. T unfolded version of u goes to u strongly, and if u epsilon converges to u strong, these all property is true for earlier unfolding, so that there was no change. Okay, so but here t epsilon u epsilon converges to u, then the average of this u epsilon tilde was the average of u, and then the derivative x3 is like that. So here your tilde is the zero extension of omega plus, zero extension of the function on whole of the omega plus. These properties were verified, and then this was the model problem. If you remember correctly, that the similar problem was explained by Rajesh. Here he just took the zero, correct? So he was homogeneous data for him. But here we consider u epsilon epsilon, as I told you that we wanted to see the idea was to go in the direction of the control, of periodic control. So we chose u epsilon epsilon, and here u epsilon is your here in the lateral part you have some scaling, epsilon to the power alpha 2. Alpha 2 is a constant, positive constant, and u epsilon is the periodic data. Okay, so this and what interesting happened here, that we got the convergence results, like y epsilon is in the if we define y epsilon in two different parts, y epsilon plus, y epsilon minus, and then y epsilon minus converges weakly in h1 omega minus, and y epsilon plus converges to h3 or y plus weakly. Okay, up so far this h is representing the width of the notch. Okay, width of the teeth. Okay, so if we allow it width to be to going to 0, or if we allow the corners, it means what will happen, that the limit problem will have issues, will have the contribution from the notch, and that will have issue. Okay, so this y minus and y plus satisfy this PD this coupled system, this system of PDE. And here, if you see, it is same like the PDE which Rajesh was showing. Okay, here if you see, this problem is this additional term is happening, which is coming from the lateral boundary data. Okay, so the lateral boundary data in omega minus, no issue, there was no problem. And if you see here, and if you the top part, if you have the normal derivative appears, and Robin condition converts into the and then you have gamma 0, you have interface condition, and these all gamma rho 0, rho 1, these all have contributions from the term from the Robin data and from the periodic data which I use there. Okay, so if you see immediately in this all, h is allowed to be positive always. H is the width of the oscillating notch. Okay, so far it was we did not write it in the paper that h is allowed to be 0. Okay, then what happens, that then you have this your theta. I was telling you that theta is the average of the periodic data which we considered there, and rho 0, rho 1 is again the average behavior of u on the interface and at the top part. Okay, so scaling was having the role there. Okay, so and this is definitely, which I was mentioning, it's written here that hx3 is the Lebesgue measure of the set yx3. So if it was the width on the reference cell of the notch. Okay, so so far we have seen the results, which started from the periodic, then we went to the locally periodic, but it was not so general locally periodic domain, but it was some sort of limit problem which capturing the locally periodicity. If you see here, go back and see this part, locally periodicity was visible in the terms of this here. Okay, so the locally periodicity was contributing. It means, and then our idea was to go to the real in the real sense locally periodic domain. Okay, and why I want to do that? Again, the motivation was coming from the shape optimization problem. So shape optimization analysis, yeah. So recently Ayyappan and class has solved this problem for the really locally periodic. It's a very fantastic result, very nice. So they actually considered any locally periodic locally periodic oscillating boundary domain, and the profile is not artificial. It is not man-made. It is just any function eta which is representing a profile, and of course there are some conditions on it, but it's quite general. So this is the domain which is really locally periodic domain, and then here epsilon has a role, like eta x over epsilon, and they proved the result for the and the limit domain, boom, here is different. In the limit domain, this is the first time I am seeing as it is not the rectangle, but it has some oscillating behavior coming from the reference oscillating boundary. And omega minus is there like always, but omega plus is not rectangular, but it's curved. So that was also very interesting so this paper became very interesting for me, at least, because it opens the door for the further to study the optimization problem. Okay, yeah. So that up to that discussion, we were so the class and Ayyappan considered the Laplacian problem. The life was for the model point of view, the life was easier, but I had a feeling always that we can also do for a non-linear type monotone problem, something like that. So when I read the paper by Antonio and Taras, I understood that I cannot get that much general results, but I can get something using the unfolding. But the idea, the shape optimization, it's clear that I wanted to understand how the profile is contributing, not only the width. I wanted more information about the profile of the oscillations. Still, I want more. It's not clear to me that how that I can, only the width can give me opportunity to compare two different profiles of the oscillating boundary. Yeah, so it's still not clear, but but slowly we are working on it. We are very slowly, but it's going on. So I considered, motivated from the work of Antonio and Taras, I considered this, and then we wrote a paper, and we considered this monotone problem with the homogeneous data. Okay, so the main result here is that main result is that u epsilon tilde converges to h u0. Here h is again the width of the reference oscillating profile, and gradient of u tilde hq bar. H is again the same. Now in the omega minus, this convergence is weak in L2. That was a crux. That was earlier we used to get the strong convergence of gradient of u epsilon, right, in the omega minus. But here we are getting weak, and the limit problem was very interesting. Okay, limit problem was very interesting because earlier we used to get two PDs, one in omega minus, one in omega plus, and then we used to get an interface condition, as I showed you before. But here we were getting a PD, which is no, just not let me tell the PD. Why? I will explain in a moment. So we got an integral equation, which was omega minus omega plus, and then we got an algebraic equation in omega plus as well. Okay, this is the all, and this was in the space of the weighted Sobolev space, where you see here L2 omega is actually the weighted Sobolev space. Okay, so why I'm writing as an integral, and we are not writing it as a PDE, because we wanted to allow H to be 0. H means the width of the oscillation. We wanted to allow it to be 0. And how we could have allowed this to be 0? Because if we allowed it to be 0, there were two difficulties. What were the difficulties? First, that if we reach up to this, how will you prove the how will you prove the existence of the solution here? If you want to prove the existence, you have to show the denseness of the C infinity function in this weighted Sobolev space. And if I don't go into the detail, I just can superficially say that we are knowing it, but we are not proving it into the papers. Okay, but recently it will appear into the paper by if it will appear into the paper by Class and Arrieta. Okay, it will appear there. So that part is done. So existence uniqueness was clear, but even the existence uniqueness is clear in the way to say how will we recover the boundary condition, right? If H is the width of the notch, at the top boundary H will become 0. So it is impossible to recover the boundary condition, correct? So in recover to boundary condition is difficult. It means it is difficult to get the limit, to write the limit PD. Okay, so we decided to leave anyway for calculating the safe derivative and all, to apply the theory of multi-scale FEM. We don't need to write it in the form of PD. We just need to write into the. So for the time being, we are happy with this. We can deal with it. And then okay, so this was the main part, and then okay, so these are the main issues which I wanted to highlight here very quickly. And then there are very few very quickly references. So many people have talked about periodic unfolding. Okay, so you have seen many references periodic unfolding. And the main references which I was mentioning about the Ayyappan's and Nandakumar's result, it was in 2017, and we started to work with the general domain, and which appeared in 2018 with Ayyappan and Nandakumaran. Yeah, so I wanted to mention a work of Jose as well here, because he considers the domain with the oscillating boundary, but with the height was of epsilon order. So he applied the unfolding for that domain, and even that work was published in 2016, and I personally like that work. Okay, so and the story of expressing the optimal control using unfolding started, as I was mentioning, in the PhD thesis of Vidhan and the Nandakumar, of course. and Rajesh, which he was presenting yesterday, the work that was it got delayed, as we understood that it got delayed because the whole history changes when you go from two-dimensional domain to three-dimensional domain. And he was keen on doing it, and he did not present that part, but that was a fantastic analysis done by him only. Okay, so the last part, the one more reference of Ayyappan is the semi-control, semi-linear optimal control oscillating boundary domain. Here we have got not the similar control we used to not use the first time with the problem with the some non-linearity, but we considered the optimal control. We could find the asymptotic behavior, but we could not say that the limit problem is actually the optimal control problem. Okay, that's all I want to say. Thank you very much for your attention.
Okay, thank you very much, Ravi, for this interesting talk. Let us wait just 1 minute if there are some questions. I don't see any for the moment.
Okay. I hope I was in time, huh?
Perfect time. Thank you.